Hello, everyone. This is an example of how to use set theory and set theory notation to compute an infinite union and an infinite intersection of sets. In this case, the sets are for every natural number n, 1, 2, 3, and so on. The sets an are sets that just contain three elements, namely the number minus 2n, 0, and 2n. And we want to describe the union of all those sets and the intersection of all those sets. So let's get started. So what is the union? In this case, the union, so if I goes from 1 to infinity, we'll start with I equals 1. That if you put n equals 1 in here, you get the set minus 2, 0, 2. And then for 2, I will get minus 4, 0, 4, and then minus 6, 0, 6, and so on. So the union of all of them, I will have 0, and then I have 2, and 4, and 6, and you see you can get 8, and so on. And also negatives, I get minus 2, and I get minus 4, and minus 6, and so on. So all in all, what I'm getting is the even integers. How do I write that in set theory notation? I would write this in this way. In the set building notation, it's m's, which is an integer, and such that m is even. And we can prove that that is the case, so that this is actually true. So we're going to prove that part right there using inclusion. So to prove that two sets are equal, each one has to be contained in the other. So first, we're going to prove that the union is contained in those integers that are even. And how do we do that? Well, just take any k in AI, and let's say not in AI, but in the union. Suppose K is in the union. Then by union, we mean is the union of all those sets are those elements that are at least in one of those sets. So then there is some n in n such that K is in one of those, but those are minus 2n, 0, 2n. And all of these are even numbers, even integers, in fact. So that means then that k is in the even integers. It's in the even integers. So therefore, with that, since k was arbitrary, that means that the union is contained in the even integers. For the opposite containment, we want to prove that if we have any even number, then that is contained in the union. So take m integer that is even. Then by definition, there is some n in integer by definition of even, such that m is twice n, and therefore m belongs to an, because an is minus 2n, 0, 2n. And since m was arbitrary, that implies that all the even integers are actually contained in the union. And that proves what we wanted to prove, which was this inclusion, which is, or this equality of sets. Great. Let's do the intersection next. So now we want to prove that the intersection of all these sets is just 0. So what is the intersection? The intersection will be, well, the intersection of A1 with A2 with A3. And we see clearly that the only element that is there is 0. So we are going to prove that this is actually true, that this intersection is exactly just the set with one element, the set with the element 0. So how do we do that? Again, we can prove inclusions. The intersection is contained in this set. Well, let's see, this I can do in the following way. The intersection of all of them will be actually containing the intersection of even just one of the sets. So it has to be contained. It has to be an element that is in all of the sets. So it has to be contained, for example, in the intersection of two of the sets. But even if I take the first two sets, we can see that the only element that is in both sets is just 0. So this is just 0. So we get the inclusion that we want. The intersection has to be contained in the set 0. And for the other containment, we just need to prove that 0 is in all of the elements, in all of the sets. So 0 belongs to AN for all N. You can see it right there. And therefore, by the definition of intersection, that means that 0 is in the intersection of all the ANs, which is what I wanted to prove, because this shows that the set 0 is contained in the intersection, and therefore we do get what we wanted to prove, which is that equality. And this is how you prove that some infinite union is a set and some infinite intersection is some other set.